Penetrating Sealer Performance Criteria on Bridges by John T. Kavern. He graduated from Iowa State with his master's and PhD, and he is on the TRB committee on emerging concretes.
Morning, everyone. I'm John Kavern. I'm the chair of Civil Mechanical Engineering at University of Missouri, Kansas City. And as we're moving into talking about sealers, I know we've got some good ones with Mario and Tim and Paul here. And so what I'm going to do is kind of queue up some of the work that we've done and really start just scratching the surface in what are we looking for in penetrating sealers. So this is really a class of materials that we're still basically in the Wild West. And everyone knows that we've got lots of different materials out there, many of them making sort of various wild claims. And so let's kind of put this in some perspective here. So what I'm going to show you here are results from a bunch of ongoing projects. So we've got stuff on Lower Verrazanos in New York City. We were pouring up at the Min Road yesterday. We've got lots of work with Iowa and Wisconsin, Minnesota on various sealers. And so we've got a few different ongoing projects, but we've got lots of sealers out on highway pavements, bridge decks for durability, for quantification. And so I will say on here, all this research is going to be sponsored by a research board, a DOT. If there's some company names or product names that come in and out of a slide, I'll just say nobody's paying for that. That's just what we're looking at here. There are we'll talk about some certain kind of classes of products, and then we'll talk about there are some products on the market where we say they have a distinct advantage and they sort of bridge between different classes, and so it's worth talking about. So, all right, we're here. We know we've spent any time with our infrastructure. We know our infrastructure is aging, and as we become more and more intelligent, we find more ways to quantify how our infrastructure is falling apart. And so we've got we've got freeze-thaw, and then we've got de-icer scaling, and then now we've got carbonation because of climate change, and we've got corrosion, and now we have the boogeyman in the room is our calcium oxychloride, which 20 years ago we never looked for, and now we look for it, and now we find it everywhere. And so, oh no, the world's literally falling apart. So, okay, we're smart. Let's take a look at this and see what in the world we can do. And we kind of say, if we're looking at bridge decks, where are some of our big issues? And we've got a lot of steel. These are high dollar pieces of infrastructure, and we are actively putting piles of chlorides down that we never used to 30, 40, 50, 60 years ago. And so we are actively harming our infrastructure, and we're doing better than we did, but it's not like we're generational leaps in concrete. We're working on it, but our ability to harm our infrastructure is far outpacing our ability to improve the durability. And so we've got de-icers, and then we throw in this crazy thing of anti-icers. So why don't I have a saturated brine and put it on my concrete while it's dry? You go, oh crap, that's a whole nother case of chemical issues I'm going to get, and now we definitely didn't design that. And so we kind of come back. So we've got some salts for sure, worrying about chlorides getting to our steel. We're definitely thinking about our critical saturation. So we've got lots of versions of this figure, but we know that Powers said if we're sort of get more than 85% saturated, doesn't matter what our concrete is, it's going to have freeze-thaw issues. And so we like to put air entrainment in it to sort of stretch that out. But that 85% threshold is a pretty tried and true fact, except for really high, really high durability or high strength concrete. So as we're moving in to talk about sealers, I'm going to throw this out here, is sealers are much like vitamins. So if I am inherently living an unhealthy lifestyle, I'm probably not going to take a vitamin to solve all my problems. Although if we're pretty good, that can enhance our health. And so All right, so let's talk about making good concrete first before we jump into sealers. So this has been a pretty generational shift if we're looking at AASHTO PP84 and the performance engineered mixtures. So instead of saying we're going to look at slump and unit weight and air, all of those tests are fundamentally over 100 years old. Haven't we learned anything since then? So yes, we've learned a lot. So we say, all right, proper drainage is really key. So if we're going to put joints in, let's make sure those joints drain. Let's not just have them as nice pools for water. Let's reduce the permeability of our concrete. We know how to do this, so let's use an appropriately low water to cement ratio. So we don't have to be pouring at a 0.5, 0.6 water to cement ratio like we used to. Use appropriate SCMs, so we're going to tighten up that structure. Well-graded or optimized aggregate gradation, really good. We want to cure it well, but not cure it too much. And we know we want to have an adequate air void system, so instead of just saying 6% air, let's fix it and forget it, let's look at the air system. Let's use some best practices for sawing. We know for a fact that if we get on that and we're sawing things out of order, we're using old equipment, we can do irreparable damage to our concrete. It can be beautiful concrete, and then we can muck it up in the middle of the night. And so we've got to do all these practices, and then we can start thinking about sealers. Okay, so we want to make good infrastructure, and then we want to make good infrastructure better. Okay, so classes of sealers. So we are sitting about a mile away. We've got kind of 4 or 5 classes of sealers. So we've got up here on, we'll say the lower, kind of lower right there, we got thick coatings, right? We've got polyesters and we've got epoxies and we've got effectively barrier coatings. We have some thinner coatings, continuous films, so we have acrylics that really, they soak in a little bit, but not a lot. They're mostly going to be some sort of a paint or continuous coating. We've got our pore blockers, so typically fatty acids or super absorbent materials. So if you think, if I took a bunch of Crisco and I wiped it on my sidewalk out front, it's going to bead water and it's going to stay relatively dry. So linseed oils and we're going to talk soy methyl ester polystyrenes later, which is effectively a pore blocker. So it gets in there, blocks those big pores, a lot of times fatty acid based. And then we have these pore liners. So if we things like silanes and siloxanes that don't actually block anything, but they're going to coat and then through surface tension are going to repulse some of the water. And so we have to think about when we talk penetrating sealers, we actually mean a whole bunch of different things. And they can be hydrophobic, they can be hydrophilic. Say, well, why in the world? Well, we can actually design a sealer that maybe grabs onto oil and greases from the roadway, holds onto that, holds onto our tire chips, and actually waterproofs it. And so you can do a lot with chemistry, but when we say penetrating sealers, I don't mean one thing. I mean a bunch of things. And that's when people are sort of showing up at your doorstep with magic juice, you got to start thinking about that mode of action. So lots and lots of different. Say, you're a mile away. This is we've got a report for Iowa DOT that's out, that'll be out soon. But just summary of lots of the different coatings we've got. And it's kind of the key, we're going to talk about this, is oftentimes for sealers, one of the party tricks is the Thompson's water seal effect. So if I'm going to put a sealer on and then someone says, look how it beads up. That is contact angle. Contact angle is good. With lower contact or higher contact angle means I've got less ability or less pressure to suck that into my pavement. I'm going to throw this out. That's one aspect. One aspect. That does not mean it's good. That does not mean it's bad, because I can dope at very, very low levels and get a very high contact angle that doesn't mean anything for durability. Okay, so that's just one thing to keep. We say, all right, so what? So what? So someone walks in your door selling some magic juice. The question should be, so how do I, number one, know it's real? Trust me, we've got lots and lots of sealers in the labs, and they range from highly effective materials to blue-colored water. There's everything and under the sun. So how do I know it's real? How do I know it's there? A bunch of these are clear. And once sort of that Thompson's water seal effect goes away because we've worn the surface, is it still even doing anything? I don't know. Most of these, we put them down, and best case, 5 years, 10 years later, we'll take a core once in a while. Okay, we need to do a little bit better if we're spending good money. We want to know if it's still working, and how can I quantify, and I'm going to say with mortal testing. Okay, so I'm going to look at just really simple tests here, because we love universities, but one of the problems with universities is somebody gives me money, I buy a massively expensive piece of equipment, and all of a sudden, everything looks like a nail. And now I'm using a piece of equipment that no DOT owns, and you just have to trust me, and you say, that's great for research, but for the rest of us, what can I do that's sort of really simple and cheap that means something? So that's what we're looking at. Okay, not to break everybody's feelings, but wait. NCHRP 244 is not a standard or a specification. And this is a report. It is a report on sealers, but I get lots and lots of sealers in that have a stamp on them that say, meet NCHRP 244. What does it meet? You're testing something on concrete? I'll get companies come in and say, hey, we want to certify it to NCHRP 244. It's a report. There are some guidelines in there. There are some tests. The tests are old. It's a 40-year-old report. The materials some of them are available, some of them aren't anymore. And so this is the thing, is if somebody comes in and says, we meet NCHRP 244, you have to ask, what piece of that? What are you talking about? It's a report. Okay, so now that I've told you that the Santa Claus and the Easter Bunny don't exist, okay, so let's actually talk about what in the world do we want? So we want to reduce our water movement in, right? So we want to keep a lower degree of saturation, so we reduce our freeze-thaw, we reduce leaching of our calcium hydroxides, we reduce changes in porosity. We want to reduce chloride movement in, obviously, because we want to reduce that time to that critical chloride threshold and corrosion initiation. We really don't want to impede the water moving out. So what if these things get saturated? If I've got a bridge deck and the top is sealed and the bottom's not, it's relatively dry, but it's still, we've got humidity coming up, and I need that to move. I need the water to move through. I do not want it trapped. We know this from the flooring industry. You go to ACI, they've been talking about bubbled floor coatings for hundreds of thousands of years. This is always a problem. So we want the water to move out so we don't have any unintended freeze-thaw issues. And we also don't want it to degrade too darn quickly, because I want to minimize a vulnerable window. So if it do have to apply, I don't want that unprotected for a long time, but I really want to minimize my reapplications as well. So, all right, we got kind of a 4-step. Let's just talk quickly through some 4 steps. And so, easy step, this is one we do look at often, is absorption. So let's look at water in. So you take a puck of concrete, you put some aluminum tape on the side, you put some plastic bag on top of it. You can have a sealed surface, and you're just going to put that in contact with water, and it's going to soak up. This is why our sidewalks outside right now are dark in color, and they'll lighten because concrete's full of a whole bunch of teeny tiny pores, sucks up water. Fortunately, it behaves in a very known condition. We have kind of a bilinear relationship of most of our concrete where we have a lot of capillary suction early, so we fill all the little pores. And then as we move into longer time, then we're going to start to fill those air entrained pores. And we get generally what we call a nick point, and you can see where we're going to transition from the little pores or the big pores, and we can take a look at what's going to happen. So what's it look like in practice? So here's absorption. So absorption uses this kind of fictional I. So if I know the mass, the density of water, and the area of my sample, I can calculate a fictional depth of penetration. It's not real, but it's comparative. We see, oh, we've got our untreated concrete here on the top. It soaks up a lot of water. And we've got a couple different silanes, so water-based or solvent-based here. And they really knock that down, that absorption way down. And we've got in here, we've got some various proprietary materials, soy methyl ester polystyrenes in there. And we got a crystalline waterproofer in there that actually sucks up some water and plugs pores. And you can say, okay, this is easy. I don't have to sort of wave my hands. If we suck up less water, that's good. That's a good thing for our concrete. Cheap and easy, doesn't require, I can get a plastic shoebox and a scale. I can do this. I can do this horizontal application. I can do it vertical application. I can try different applications. And so if we look at, we did some work for Wisconsin where we looked at a bunch of different application rates, 100, 200, 400 square feet per gallon, so a lot to a little. Right after 24 hours, we're going to saw the concrete, wash it, and we're going to apply it immediately to 1-day-old concrete. We're going to apply it to dry 7-day-old concrete, or we're going to do it 2 applications. 7 days, let it cure, apply it again 7 days, and we can measure. So here is the kind of the green. See, the green on the screen means every single permutation for that solvent-based resulted in a significant, so greater than 50% drop in absorption. Some things we should have pause. Okay, so I can fool this test, especially with silane. I can take a 1% silane, I can put it in a solvent, I can spray it on my surface, and at least initially, I can fool this test. Doesn't last for a long time, but it is something to think about. But cheap and easy test. We can look at, here's water-based silane, really good performance. We've got our soy methyl ester polystyrene. We've got real nice performance. This was a raw lithium silicate. So we didn't really talk about pore refiners, but if I put a densifier on my concrete, I'm going to consume those extra calcium hydroxide, make more CSH gel in the pores so the pores are smaller. And we've got our crystalline, that crystalline waterproofer didn't work at all. So collected a bunch of data, doesn't really cost me anything. Pretty interesting. I'll say step 1.5. So this is 3 different concretes. So the one on the left is concrete that had a marginal air system. The middle is an oxychloride susceptible concrete, and the right is a decracking susceptible. So this is work out of Iowa. So Iowa says everybody does their testing on really good concrete. We're not worried about good concrete. We're worried about crappy concrete, and nobody in the field wants to make really bad concrete. So we made bad concrete and we tested it. And you can look at that absorption trend, and then we take it, and after we're done soaking up water, we just put it in the environmental chamber, we dry it out, and we measure the desorption trend. Again, not real expensive, but quite telling. Our silanes for all 3 of these, really low. We absorb less, we desorb, and we can look at, this is our Pavix, which is a super absorbent material that has a potassium siliconate, so it's hydrophobic and absorptive. And we've got our soy methyl ester polystyrene, and we can see they absorb less, but we're going to dry. We're not really impeding drying for 2 of those. But our pore blocker over here for our decracker did impede drying. Okay, so regular concrete, that's good. If I have concrete susceptible to freeze-thaw damage, such as a decracker, maybe we don't want to be using a pore blocker in that situation. So again, we can take a look. You can evaluate lots of different ones, but again, we're still cheap and easy. I can take that and I can then saturate the sample after we're done. We can vacuum saturate or put it in a bucket. And if you put it in a bucket for 30 to 60 days, it'll get to full saturation or just about as close. And then you can calculate your, instead of that fictional I, you can calculate your percent saturation. So how long did it take you to get to that 85% saturation? And my other treatments what did that do for my extension to life cycle? So again, I'm talking a 5-gallon bucket, so we're not spending a lot of time. And then we can do projections and say, holy crap, we've got soy methyl ester here had a 9 times increase to time to critical saturation. Or, oh, what if we just used a curing compound? Yeah, curing compound didn't really do anything. We didn't have any improvements. And we can kind of see siloxanes or different silanes. We got significant increase to the time to critical saturation. That's pretty important. That's, again, have not spent a lot of money. Other thing we want to do is we want to look at how do these things dry. And so let's bring them back to all to the same place. So let's soak them. Let's seal one side, the unsealed side with plastic. We've got the sealed side pointed up. And let's look at time. How do these dry? So sort of the top, these are our inadequate air, oxychloride, and decracker. The top row is 0 to 1 day, and the bottom is 0 to 15 days. You can kind of see this inadequate air sample dries really, really quickly. Our sealers slowed down that drying process. So if we seal and saturate our inadequate air, actually our sealers are going to hurt us in that case. Oxychloride here, we've got real nice drying behavior, but we can see in this 15-day, we've got our absorptive, water absorptive material gives off the water, trends very, very much with our control. We see in this case our silane and our pore liners and our pore blockers here are slowing down that evaporation process. And so, again, pretty cheap and easy, but if I have some susceptibility in my mix to freeze-thaw damage, now we can say, you know what, maybe we don't want to be using some of these on certain concretes. Step 3, contact angle. So this is, I can buy really expensive equipment to measure contact angle, or we can use a camera and free program on free software on the internet, and we can measure that contact angle to see how hydrophobic the material is. We can relate that hydrophobicity to absorption. So again, if we care about that, very, very easy to do. Chloride penetration. So here's our AASHTO T259 T260 where we do our 90-day pond test, and we can do it on our sealed samples. And then you're going to grind, and we're going to look at sort of that 0 or 1/8 inch to 1/2 inch as a top, and then 1/2 inch to 1 inch, and you can get some chloride penetration. So we say, oh, silane really knocked us down. Silane applied moist knocked us down. Siloxanes didn't really do a whole lot, little bit. Or soy methyl ester did well, and we can look at this and we can say, is this reducing my chlorides? I will sort of throw out the caveat that this test is far too coarse for actual work, actual utilization. So it says, what's the average in this 1/2 inch and what's the average in that 1/2 inch? There's a lot more nuance in there. So if we run the ASTM test, we do it every couple millimeters and we get a nice curve. And so I'll say, if you're doing it as maybe an acceptance in that top, okay, you've got to run the ASTM if we're doing any sort of real life cycle assessment here. So those are all pretty quick and easy. The kind of last thing I'm going to throw out there here is the boogeyman. And so if we've been around anywhere, we've got this oxychloride discussion. And so if I have extra calcium hydroxides in my concrete and I apply magnesium chloride or calcium chloride, I get this expansive transient mineral that's calcium monooxychloride, and it is, what we're looking at is a lot of the things we've been thinking is de-icer scaling and de-icer attack is a different mechanism. And oxychloride's scary in that it happens between 40 and 50 degrees Fahrenheit. So this is one, we apply a bunch, and then typically what I'm going to have on the university is it gets humid in July, we get a cool night in July, and all of a sudden I have a bunch of de-icer damage in July. So we're looking at oxychloride testing. So this is more complicated. This is a low temperature scanning DSC. But we can see we've got different densifiers. We've got silanes. We've got our Pavix. We've got our soy methyl ester. Across the board, no matter how we do it, they do a really, really good job of knocking down that oxychloride potential. And so this is pretty good. So now as we're tying things together, now we can start looking at sealers in with our diffusion testing for life cycle. And so ASTM and ACI are using developing some new methods which allow the use of sealers so we can start doing some forward projections. So we know we've got a ton of different chemicals and products exist which fall into that penetrating sealer, but they are different. They do not function the same. Some are good applied early, some are good applied late, some are good for bad concrete, some are not good for bad concrete. 244 doesn't describe this adequately, and so I'd say at a minimum, be looking at absorption and desorption, be looking at desaturation, can measure contact angle and chloride penetration, all relatively cheap. If you really want, you can look at chloride initiation, you can look at de-icer scaling, one-dimensional freeze-thaw, and oxychloride could be beneficial as well if we're going to sort of do some qualifications. And so we'll throw out, I mean, the body of research is growing, and it all is looking really good. So we say the value proposition, the technology, and the test methods are here. And so let's use it, but it's not a panacea for bad concrete. Let's make good concrete, and then let's make good concrete better. So with that, here's a picture. We were putting down our bridge deck samples up at the Min Road here, sort of trying to sneak it in before everything froze, and we'll be hitting them with a pile of anti-icers here this winter. So.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.